start. So remember, yesterday I introduced two different discrete objects which were the simple random walk and percolation. And from there, I gave you two features of scaling limits which we now want to use to describe the possible scaling limits. So there was the domain Markov property, which says that if you condition some complicated object by some piece of it, what you see on the outside of what you know has the same distribution as what you would get if you sampled the object in the complement. And I will give a more proper definition a little bit later. And a conformal invariant. So these are two features that, so this one was clear for percolation, and this one was, well, easy to prove for Brownian motion. And the question is, if you have some interface model, which means a curve in a domain omega, which is random, which satisfies the domain Markov property and which has some conformal invariance in the sense that if you define it in some other domain, you get the same thing as if you mapped omega by a conformal map. So if you have an interface that satisfies these two properties, the question is, can we identify so an interface gamma? Can we identify the probability distribution of gamma using only these two features? And the answer is almost. And we'll see it's true essentially up to a one-parameter family, and this is what Schramm did to define the SLE process. So before we do that, let's fix one particular domain, and today I will tell you about Loewner chains in H. So H is the upper half plane. So it's R times R plus. But it's really seen as one half of the complex plane, so it's really a piece of, well, it's a piece of the complex plane. So here is H, so that's the upper half plane. And we have some interface, so some curve. So gamma is a curve in H bar. So it's allowed to touch the boundary. It starts here. So let me list a few features of gamma that we will assume just to make the picture easy. So we are assuming that gamma 0 is 0. So the curve starts here. So it starts here. For the moment, I will assume that gamma is simple. So if S is not equal to T, then gamma S is not equal to gamma T. And I will assume that gamma does not touch the boundary, again after leaving it at 0. So if S is positive, then gamma S is not a real number. So gamma looks like this. It goes into the complex plane and it does something like that. So typically this is the kind of interface that we would expect from the scaling limit of a discrete model in the upper half plane, except for this assumption here, which is the fact that gamma is simple, because well, if you do the scaling limit procedure for percolation, for instance, because the percolation has all these finite loops, it's not difficult to predict that the scaling limit will have double points corresponding to these loops. So it will not look like this, it will look like this. So it will start here and it will touch the boundary, it will touch itself. So this is the real picture that you should maybe have in mind if you think about percolation. So it's not a simple curve, but still, because it's an interface, at the discrete level it is a simple curve. In the dual graph we had a simple curve. It came back to distance delta of itself, but it was still simple. So what you get in the scaling limit is not necessarily a simple curve, but it's at least a non-self-crossing curve. So I'm putting it aside. Everything I will say today essentially is true for non-self-crossing curves, but already defining what it means to be non-self-crossing is not completely clear. It's not completely difficult either, but it makes the picture a little bit more complicated. So let's focus on simple curves. So here is some interface in H, and the question is, how can we use the domain Markov property and the conformal invariance to obtain information or to get a natural way to describe this curve and to identify its distribution. So the main idea, which is kind of natural if you look at this part here, at the conformal invariance, is to describe gamma using conformal maps. So this is what we're going to do, and this is actually something quite old. It was done by Loewner in the 1920s. And so we'll spend some time rehashing something about the Riemann mapping theorem and about how to normalize maps and everything, to be able to get a theory of how to describe a curve in the plane using a family of conformal maps. So the key picture is the following. This is a curve. Let's look at the point gamma t. It's some point on the curve. So this is 0, which is gamma 0. And let's say we just, for the moment, want to define gamma up to time t. So we have this piece of the curve up to gamma t. And then we have the future of the curve, and we don't care about the future of the curve yet. So to define that using a conformal map, there is essentially only one thing you can think about. You can define ht, which is h minus gamma between 0 and t. So it's what remains from the upper half plane when you remove the first piece of the curve. So it's here. And ht is some simply connected domain. So by the Riemann mapping theorem, there exists a map, gt, which is a conformal map from ht back to the upper half plane. So there exists gt, which maps ht conformally to h. So conformal. And so it sends ht to h. It sends the boundary of ht to the boundary of h. And here notice that the boundary of h is very nice and smooth. So g does extend to the boundary, with a little technical point that you need to distinguish 2 points on the two sides of the curve as 2 different points of the boundary of ht. But up to this, g extends to the boundary. And so what it does is it sends the boundary of ht to the boundary of h. It sends the tip of the curve, the gamma t here, to some point here. So this will be gt of gamma t. The left side here of the curve will be sent to something on the left here. The right part will be sent to something on the right. And essentially this is gt of 0 minus. It's the image of this corner here by gt, and this point here is gt of 0 plus. And then this here, this whole half line is gt of r minus, and this is gt of r plus. And the last bit of the picture is the future of gamma, and the future of gamma starts from gamma t and goes somewhere. So if you map it by gt, it starts here and it goes somewhere. So that's a picture I will draw maybe 50 times today. It will always be the same picture. You have something in the plane, you look at one half, you remove one half by conformal map, and you see what happens to the next piece of it. So, well, the first thing we need to be careful about is, no, first the real reason why this is interesting is that once you have G like this, you can always look at G minus 1. And G minus 1 is a conformal map from H to HT. So if you know G minus 1, you look at the image, it gives you HT and it gives you gamma because that's just the boundary of HT. So the whole geometry of gamma as a simple curve is contained in this map GT. So it's like a bijection between a set of simple curves and a set of conformal maps. So gt minus 1 gives gamma t back. So this statement is simple when gamma is a simple curve. It's not true that from one of the GTs you get exactly the whole curve up to time t if the curve is not simple, because you have no clue what happens inside the bubbles. And so that's the main reason to look at simple curves for now. That it's simpler to come back from GT to the curve if the curve is simple, and if you know that a priori. So the first thing we need to be careful about is how to choose the GT. So what about the choice of GT? So the Riemann mapping theorem tells you that whenever you have two simply connected domains, so Riemann mapping theorem says that for any omega and omega prime which are domains, and recall I'm always assuming that the domains are strict subsets of C, so it's not C itself. So there is phi which is a conformal map from omega to omega prime. And in fact, there are quite a few of them. There's a 3 real parameter family of phi, which are conformal between omega and omega prime. So there are essentially 2 ways to make phi unique. So phi is uniquely specified by essentially giving 3 real conditions. If you want, 3 is the dimension of the conformal group. So it's the number of degrees of freedom you have if you want to choose a conformal map. So this will be, well, what we want to do is to fix 3 real conditions, and what it means, it can mean one complex number, one complex condition and one real. So typically you fix 1 point in omega and 1 point in omega prime, and you fix, so this will be a complex number, and maybe 1 point on the boundary and 1 point on the boundary. So fix w in omega, w prime in omega prime, and fix x in the boundary of omega and x prime in the boundary of omega prime. So this is given by one complex coordinate, this is given by one real coordinate along the boundary, and this is what I mean by one complex and one real coefficient. And then there is a unique conformal map from omega to omega prime. So conformal, so a bijection which is holomorphic in its variable, and it's made unique if, so we want it to be such that phi of w is w prime and phi of x is x prime. So we know existence and we have uniqueness if we fix the image of one point inside and one point on the boundary. And the other thing we can do is to have three real conditions. So typically we will fix 3 points on the boundary, so A, B, C in the boundary of omega, and A prime, B prime, C prime on the boundary of omega prime. And you need to be careful that they are chosen with the same order along the boundary. So same order, because you know that the order will be preserved by conformal maps. And if you fix these 3 points and these 3 points, then there exists again a unique phi from omega to omega prime, which is conformal and which sends A to A prime, B to B prime, and C to C prime. So this is what you can do typically if you want to specify out of all the conformal maps between two domains, if you want to specify one of them. So let's see how to apply that to this question of specifying GT. So just one definition. It's not a standard definition in the literature, I think, outside of what I saw in SLE, but it's kind of usual in SLE. So a L will be for us is a compact set, is a compact subset of H bar whose complement in H is simply connected. So with H is a compact subset K of H bar such that H minus K is a domain. So it's something that you can remove from H to obtain a domain. And for now, I will assume that K is connected. The fact that K is connected is not essential. The fact that the complement of K is simply connected is what is relevant. But K is compact with a simply connected complement. So it looks like that. So this is a typical, this is what you should have in mind. It's some compact set that touches the boundary and leaves something in the complement which is a domain. So the key example will be gamma between time 0 and t. If gamma is a simple curve, the path gamma up to time t is a compact set. It touches the boundary, the complement is simply connected, so it satisfies all these conditions, and it's a hull in H. If gamma is not a simple curve, then you have to do what I did yesterday from the Brownian motion. You have to make the complement of K in H connected again, so you have to fill all the bubbles that are closed by gamma. And this is what I called the hull of Brownian motion, and we'll come back to that. From any curve, you can construct a hull which is obtained from the curve by, well, making it hull by making the complement connected. So this is a hull, and we want to construct some conformal map from the complement of K back to H. So we want to construct GK which maps H minus K back to H. And again, here it will extend to the boundary, and it will send the boundary of K somewhere here. So this will be GK of the boundary of K. So we know that such a map exists by the Riemann mapping theorem. If we want to make it unique, we want to normalize it in one of these two ways. So what do we have at our disposal that would make this natural? In H, drawn like this, well, there's really no special points except maybe the point at infinity. So the only natural point to choose if we want to uniformize it like that and specify G is to look at the behavior of G at infinity. So look at Gk at the point at infinity. So infinity is a point on the boundary of the domain. So it will be one of the real coefficients here. So what can we impose on G concerning its behavior at infinity? So the first condition is that we want Gk to be the identity if K is empty. We want that encoding something which is empty gives a trivial map. So in particular, we want that G goes to infinity at infinity, that if you remove something very small, it will not be seen by G if you look far enough. So the natural thing to say is that we want Gk of infinity to be infinity. And what this really means is that the limit at infinity of Gk should be infinity. So this is specifying the image of one boundary point to be one of the boundary points in the image. So that's one real coefficient. Second thing, now we would like Gk to be as close to the identity away from K as possible. So the second thing is that, well, typically we would want Gk of Z to look like Z at infinity. So we want the expansion of Gk at infinity to be as close to the expansion of identity as possible. And the first thing to try to impose is to say that Gk of Z is equivalent to Z at infinity. So that the limit of Gk of Z divided by Z, so Gk of Z over Z goes to 1 at infinity. So why is Z and not something of higher power, or why this behavior? That's just because infinity is a point on the boundary which is smooth, so you know that G will have to be differentiable at this point on the boundary. If you're not careful, if you're not comfortable with points at infinity, you can always map everything by 1 over Z and map infinity to 0, and then you know that if you have a conformal map on a boundary with a smooth on a domain with a smooth boundary, then the derivative of the conformal map extends to something which is also smooth on the boundary. So this here is another coefficient here, but because we are looking at the boundary of a domain which is the real line, this has to be, this limit, if it exists, has to be a real number. So this is one more real coefficient. So we need 1/3 real coefficient. And since we are looking at the expansion at infinity, it's natural to look at the next term in the expansion. And at infinity, the next term will be the constant term. So what we do, we look at Gk of Z, we remove this term. So this gives the constant term if we let Z go to infinity. And we fix this to be 0. Again, this would correspond to translation around. Changing this corresponds to adding a constant. It's a translation along the real axis. So again, this is one real coefficient. So 1, 2, and 3 are real coefficients, and specifying these conditions is enough to make Gk unique. So to sum up, so here's the proposition. Whenever K is a hull in H bar, there is a unique conformal map, GK, which goes from H minus K back to H, conformal, and with the expansion, if we put everything in one formula, so such that, so GK of Z at infinity has the expansion, which is Z plus something of order 1 over Z. So all the terms, the first terms of the expansion are the fact that this goes to infinity with speed 1 and with 0 translation. So this is the way we will normalize conformal maps. Whenever you have a hull, you have exactly one conformal map that does the job here, and with this normalization at infinity. So what next can we say about that? Well, this term here in 1 over Z, in fact, it's something over Z, because it's just the coefficient of the expansion in degree minus 1. So we can always write GK of Z is Z plus something over Z plus big O of 1 over Z squared at infinity. So just to give a name to this coefficient here, and A of K is called the half space capacity of K. So you should think of it as some measure of the size of the set K seen as, well, seen from the conformal point of view. And here's a lemma, or here's an exercise, if you want. The exercise is to show that A of K is positive as soon as K is not empty. So of course, if K is empty, GK is the identity, so A is 0. The exercise is to show that as soon as you remove something non-empty from the upper half plane, the capacity here is strictly positive. So let's play a bit with these maps, because it will give us some information about what to do next. So we will want to apply this to curves like this, which are scaling limits. So the first thing to try to look at is how the choice of GK responds to scaling. So scaling relation. And by scaling relation, I mean, so again, let's take K hull. So it comes with this conformal map GK. And let's fix lambda positive. So it will be a scaling coefficient. We can scale K by lambda to get, well, if you keep in mind that lambda is smaller than 1, for instance, you get a smaller hull, which is lambda K. And you can consider the map G, which removes lambda K from the picture. Again, lambda K is just a scaling of K, so it's a hull. So here is what we have. This is K. This is lambda K. And this is the upper half plane. And so if we remove K, we get H minus K here. This is H minus lambda K. And we have two conformal maps in the picture, which are GK and G lambda K. And the question is, how are gk and g lambda k related? So another way of asking the same question is, if you know gk, how can you compute g lambda k? So this is not very complicated. How do you cook up a conformal map from h minus lambda k back to h if you have a map like this? Well, the natural thing to do is to use gk as a building block of this map here. So you want to go from h minus lambda k to h minus k and then apply gk. So to go from here to here, there's essentially one choice. You just divide everything by lambda and then you apply gk. So let's try. Let's look at h of z, which is gk of z over lambda. So it's a composition of conformal maps. It maps the complement of lambda k back to h. So h is a map from h minus lambda k conformal back to h. So it's one of the conformal maps here in the question. It's not the right one, because if you look at the expansion at infinity, so what you do, you know the expansion of gk at infinity, and you plug z over lambda in it. So what you get is z over lambda plus a of k divided by z over lambda plus big O of 1 over z squared. So it's wrong because this is not the correct term for the degree 1. If you want the correct normalization, you want to multiply everything by lambda to get the correct expansion. And if you do that, well, you will see that this is affected as well. It's multiplied by lambda. But the shape of the expansion is the same as what you want to choose the g sub lambda k. So what we get is that g lambda k is the same as lambda h. There are two conformal maps from h minus lambda k back to h, and they satisfy the same criteria. If you look at the expansion of lambda h, it is something like z plus 0 plus something over z. So it has to be the same function as g lambda k. And in particular, so to sum it up, this is lambda times gk of z over lambda. So this is what we get from the uniqueness in the Riemann mapping theorem. If we want to identify g lambda k, we build a candidate which is a conformal map with the right expansion, and by uniqueness we know it's the same map. So we get this. So in particular, if you look at the expansion, well, the expansion of this at infinity is z plus a of lambda k over z plus big O of 1 over z squared. And if you look at the expansion of this at infinity, is what we just computed. It's this times lambda. So what you get is z plus, so there will be one lambda coming from here and one lambda coming from here. So there will be a lambda squared a of k divided by z plus big O of 1 over z squared. And so in particular, what we get is a scaling relation for the capacity, which will tell us that the capacity of lambda k is just lambda squared times the capacity of k. So it's one feature of the capacity which comes directly from the uniqueness of the conformal maps with this normalization. So really, you should think of A of k like the surface of k, like the Lebesgue measure of k. It scales at least the same way. of course, it's not equal because it's defined by conformal maps and it's not directly related to the surface, but it gives you some intuition of why it's a natural notion for the size of K. So maybe, what did I want to say? Maybe a few examples of such maps would be interesting. So, just two examples that will be relevant for what follows. So what are the simplest domains and the simplest hull that you can consider? So if you have the upper half plane and you want to remove something from it that has a simply connected complement, so the first thing you might want to remove is just a straight vertical segment here. So this will be point I. So if you want to go conformally from that to H, this will be G of the interval between 0 and I. Well then, you can do that actually explicitly. And if you want that as an exercise, you can show that G0I of Z is exactly given by square root of Z squared plus 1. So it's not really difficult to do if you have the solution here. What you do is you build this by blocks and you see what happens to this domain. So you first apply Z to Z squared and you show that this will essentially double the argument, so it will fold the left part of the boundary back to the right half, and it will turn this interval into 0 minus 1. So you get the whole plane minus the line between minus 1 and infinity. Then you shift that by plus 1 to map the image of I to minus 1 to 0, and then you take the square root to refold it into the upper half plane. So it's better to do a picture yourself to familiarize yourself to the construction of such conformal maps. But at least it's easy to check that this has the right expansion. You can factor the Z out, and it's Z square root of 1 plus 1 over Z squared. So what you get is that this one has capacity 1/2. So A of 0I is 1/2. The second thing that you can remove, which is more relevant for what we are going to do, is so the other simplest thing that you can remove from the upper half plane is just a piece of a disk. So this here will be the circle centered at 0 and of radius 1, and K is just a half disk. And then second exercise, in that case G of Z is just Z plus 1 over Z. So in some sense it's the simplest conformal map with the expansion that we want. If we want the expansion to start like Z plus something over Z, well, the simplest case would be to have the expansion exactly equal to Z plus something over Z. And by the scaling relation that we just got, we can always assume that this something over Z is 1 over Z. So this is some natural conformal map. And it turns out that this removes half a disk from the upper half. Okay, so these are two exercises that, well, once you have the answer, once you know G, it's not difficult to convince yourself that the hull corresponding to G is here it's a segment and here is a half disk. Okay, so now what we have is, so remember we want to describe a curve that grows in the upper half plane in terms of conformal maps. So recall, so we have gamma in H bar, but gamma t is in H if t is positive. So this is the curve that we want to describe. And I will draw it again. This is gamma, this is gamma t. And for each t, gamma between 0 and t is a half. So for every t positive, gamma between 0 and t is a half. So let's define ht to be the complement of this half. So it's h minus gamma between 0 and t. And now there is a unique conformal map with this expansion here. So there is a unique map that maps back. So this is ht back to h. And so there is a unique gt which maps ht conformally to h with the expansion that gt of z is z plus something over z. Let's call it a of t over z plus big O of 1 over z squared. So what this means is that we started from a curve gamma, and what we got was a family gt of conformal maps, and for each t we have a unique map if we fix this expansion. So now we are getting somewhere. We started from a curve, we have a family of conformal maps, and we have this function a of t, which is the capacity of the piece of the curve up to time t. So one more thing I want to say that I said yesterday. When we looked at the conformal invariance of Brownian motion, there was this whole question of how to parameterize the curve. And if you map a Brownian motion by a conformal map, what you get is Brownian motion, but there is a time change. And we wanted to have simpler statements, and you get simpler statements if you want to ignore the time parameter. So what we want to ignore the time parameter on the curve gamma. So what it really means is that if you have the same curve but parameterized at a different speed, you really want to identify them and focus just on the geometry of the curve. And what that means is that maybe given a curve, there is one natural way to parameterize it, which will be easier to treat for what follows. So we want to ignore the time parameter, or equivalently, we want to define a natural parameter on gamma. Well, for those who know about SLE, this is not the natural parameterization of SLE in the sense of Loewner, so it's let's call it a conformal parameter. So here's one quick computation. That I'm going to do. It's a very easy computation. It tells us what happens to the parameter A if we compose two conformal maps. So let's look at a map which is z plus a over z plus big O of 1 over z squared. And let's compose it with a map which is z plus b over z plus big O of 1 over z squared. So if you want to compose two maps, you just replace z by this on the left. So what you get is that this is z plus b over z plus big O of 1 over z squared plus a over this. So z plus b over z plus big O of 1 over z squared plus big O of 1 over z squared. So this is of order z, so if you plug it in the big O, you get still something like 1 over z squared. Okay, and then you expand everything to get a nice expansion. So this gives you z plus b over z. And this, if you look at the expansion of this, you can take a over z out of it. And you get 1 over 1 plus something of order 1 over z squared. So this again is 1 plus big O of 1 over z squared. And there is a big O of 1 over z squared. So if you put everything together, what you get is that this is z plus a plus b over z plus big O of 1 over z squared. Okay, so far this is just a computation, but it tells us that the capacity is something which is additive under composition of conformal maps. So the capacity is additive and recall that there is this exercise that you have to do, which is showing that the capacity is strictly positive. So this means that essentially we want to say that the capacity will look like time. It's something positive and it's additive if you compose. So it's tempting to try to use it as a parameter. So if you really want to use it as a parameter, well, we need a few things, but here's the lemma, which is that the map that to every t associates the capacity of gamma up to time t. So A of gamma between time 0 and t is continuous and strictly increasing. So once we have this, it means that really A of gamma between time 0 and t, so this parameter A of t here, so that's what I call A of t. This can be used as a time change on gamma, and we can essentially specify the parameter on gamma by specifying how A of t will grow as a function of t. So how do you do that? So proof of that, let's look first at the fact that it's strictly increasing and everything else will follow from that. So here is another picture that will come back many times in the following lectures. So I want to do it first today. So here is gamma, and here is gamma t, and here is gamma at time t plus s. And we would like to compare the capacity A of t to the capacity A of t plus s. So what can we do for that? Well, we have one natural conformal map, which is the map from ht to h, which is gt. So gt, it maps ht to h. It maps the curve between 0 and gamma t to here. So this is gt of gamma t. And it maps the future of the curve after time t to a curve starting at gt of gamma t and going into the upper half plane. And this has, well, this gamma t plus s has some image. So g t of gamma t plus s. So this is the map gt. It looks at the first behavior of the curve for times between 0 and t. Okay, we have another map which is natural, which is, now that we are here, we have this curve here, which is gt of this piece of the curve. Maybe I should use a different color. So this is the piece of the curve between times t and t plus s. It's mapped here by gt. And so you can see on the picture, and it's easy to prove, that the image of this segment of the curve by gt is a hull. It's connected because it's the image of a connected set. It starts on the boundary. It's still simple curve inside h. So this here, let's give it a name. So here, kst, which is gt of gamma between times t and t plus s, is a hull. So if it's a hull, it's here. It comes with a conformal map which removes it. So there is this map here, GST, which is the map that removes the hull KST from the upper half plane. Okay, and it does something like that. It removes the hull into something on the boundary. So this has to push the images of these two intervals away from the points at which everything is happening. So this should be red, like this. And this is the image by GST of the future here. So we have this nice composition of GT and GST. And if you look at what this composition does, well, it's a conformal map from the complement of all of this up to time gt plus s to h. And the expansion is given by this computation here. So it's an expansion which, which is of the form z plus something of a z. But we have another map that does exactly the same, which is a conformal map between the complement of this up to time t plus s and h, which is just the map g at time t plus s. So this is the map g t plus s. And it has the same expansion. So by the uniqueness property, what we have is that, so maybe I should get a new board for that. So what we get is that the map G T plus S is just the composition of first doing GT and then doing GST. Okay, so if we look now at the capacity term here, here we get A of T plus S, and here we get a composition of two maps. So we apply our computation here. The 1 over z term of GT is A of T, and the 1 over z term here is the capacity of the set KST. So we get something like that. So this tells us that the increment of A between times t and t plus s is itself the capacity of something. And we know that capacities are strictly positive. So from that we get that A of t plus s is strictly bigger than A of t. Okay, if we want the continuity, what we want is to know that if you take t and s which are close to each other, then the increment is small. So what you want is that if you take a small set here, you map it by G, it's a small set. Well, you want that the capacity of something small is itself small, because if you have this, then it will tell you that the increment is small. So for continuity, so we have a bound, for instance. We know that the capacity is something increasing by exactly the same argument here. If k is contained in k prime, then the capacity of k prime is bigger than the capacity of k. So, for instance, by this example here, we know that the capacity of a set is bounded by some constant times the square of its diameter. So if k is small, the capacity A of k is small. So, for instance, A of k is less than c times the diameter of k union 0 squared, something like that. Let's see, k squared. Okay, so I don't have time to do the details, but the main point of the proof of the lemma is to prove this additivity formula and to write the increment of A as the capacity of something. And then if the curve is continuous, you can, by taking S and T close, you can have something small. And if the something is small, this A is small, so it gives you the continuity of A. Okay, I'm not sure how much time I have left today, but there's nobody in charge, so I will decide that I still have 3 minutes, unless you are craving coffee. But so what I want to get at is A is continuous strictly increasing. So up to a reparameterization by the inverse of A, so we can assume up to a reparameterization of gamma that A of t is always equal to 2t. And we'll see later why this 2 is here. It's just some artifact from the history of Loewner chains. So if we want to only know something about the geometry of the curve, it's okay to reparameterize it. And we can choose the parameter like this. So in other words, we have gamma, we choose the parameter so that A of t is 2t, and so we have gt, which goes from ht to h conformally, and it has the expansion that gt of z is z plus 2t over z plus big O of 1 over z squared. So we started from curve and we got this nice family of conformal maps. And the main thing I wanted to state today is a theorem from Loewner. So this is what was done in the 20s, is that in this framework, so in this setup, there exists a continuous real valued function, so beta t, positive, so it's continuous and it's real valued, And it's such that whenever you choose z in HT, so whenever z is in the domain of GT, you have the following equation. The time derivative of GT of z is 2 over GT of z minus beta t. And with the previous notation, in fact, the beta t is nothing else but the GT of the tip of the curve. So it's this point that was here. So this point is actually this beta t. So I will give you some indications of why this theorem is true tomorrow, and we'll go from there to continue in the plan that we have. Just one remark and one indication of what I will do tomorrow. The one remark is that we wanted to describe the geometry of a curve in the plane, and we reduced the curve into this function beta t here. And you can see that if you know beta t, you can solve this differential equation to reconstruct GT, and if you know GT, you can reconstruct gamma. So all the geometric information about gamma is contained in beta, but now beta is a real valued function, which is a much simpler object. So this really reduces the dimension of the things to describe a lot, because now if we want to identify a scaling limit under these assumptions, all we have to identify is beta, which is a real valued function. And that's much easier. So tomorrow, what I will do, and I want to give the definition of SLE today because now it fits. What I will prove tomorrow is the theorem of Schramm, which says that if you have conformal invariance plus the domain Markov property, then beta t is square root of kappa times bt, where bt is a real valued Bonan motion. And this is what is known as SLE kappa. So maybe I shouldn't have written this, but because it's spoiling the fact that this is what will come up tomorrow. But SLE is what you get if you start from the Loewner equation here. You put square root of kappa times Bonan motion here, and you solve it. And that's what we'll study for the remainder of this course. Okay, now it's time for coffee. Questions? Yeah.
Is GT of gamma equal to 0 continuously in the drawing?
This point here?
Yeah.
It's not 0. It's prescribed by the geometry, so you cannot say it's 0 if you have symmetry, so it's 0 in the case that is here, if you go straight. And no, it's this beta t. So if it were 0, you would get this equation, and solving it, you would get square root of z squared plus something times t. So you'll see tomorrow. I will look at the position of this point more precisely tomorrow to get the theorem. Okay?
You just said that we have a coffee